Hello, I am Konsta Huhtala from Tampere University. This talk is about approximate local output regulation for a class of nonlinear fluid flows, and it is a joint work with my supervisor, Paunonen. Let us start by going through the structure of this talk. So for the most part, we will focus on a single PDE example, which we present in the problem setup section, and we also specify the actual regulation goal, which is here the approximate and local nature. Then in the system analysis, we present the required mathematical framework and also show that the handled PDE fits into this framework. In controller design, we present the controller in a quite generic level and focus on discussing its relevant properties when it comes to output regulation. And then we have a numerical example, including a simulation where we see how the controller actually performs and how approximate the tracking ends up being in this case. And finally, in the conclusion part, we discuss to what kind of systems these results can directly be applied to. So let us focus our thoughts on the Navier-Stokes equations on a two-dimensional domain omega with a C3 boundary gamma. Up until this point, we have the standard Navier-Stokes equations with the viscous term, the nonlinear term, and the pressure term. Then from there on, we have the control term Fu and the disturbance term Fd, and these we'll return to later. Finally, we have the time-independent body force denoted by Fb. Then on the second line, we have an incompressibility constraint here, usually a boundary condition here, and finally an initial condition. The achievable output tracking with this control method is local in the sense that the initial state as well as the reference signal should be small enough for the control to work. And then the control is also approximate in the sense that we do not actually necessarily achieve convergence of the system output Y to the reference output YR, but we only have the convergence for some harmonics. But we do get to choose which these harmonics are. We employ the framework of regular nonlinear systems introduced by Navier and Bentzmann, although we do not do so in its full generality, but rather we focus on the parts of the formulation which are relevant to our work instead of the full general framework of the nonlinear systems. Regular nonlinear systems are defined in some Hilbert space X. And we have, as in the case of abstract linear systems, we have the system operator A, the control operator B, and the disturbance operator BD. But then we also have the nonlinearity F, which is applied by another linear operator Q. And then each of the triples in the point 1 should be regular linear systems. So you can have as the input operator either the control operator, the disturbance operator, or the nonlinearity applying operator Q. And all these triples should be regular linear systems. And when it comes to the nonlinearity F, it should be locally Lipschitz from the state space to some Hilbert space V. And finally, for the observation, we also included the lambda extension of the observation operator, although, as we will see later, that will not be very relevant for this particular problem. Choice of the state space is a very central point of this work, and for that we make use of the Stokes operator. So not only does the Stokes operator generate an analytic semigroup on this L2 type state space, but here more importantly, it allows us to define a scale of spaces in that we use fractional powers and their domains of the Stokes operator to define the state space X. So here, the Leray projector P enforces the incompressibility condition of the Navier-Stokes equations, and then the state space ends up being presented very similarly to the domain of the Stokes operator, except that instead of H2 here, you would have H1 plus 2 delta. So our motivation behind choosing the somewhat unorthodox state space X is to satisfy the local Lipschitz requirements of the regular nonlinear systems. And for that, we now choose the Hilbert space V as a larger space, but still defined using the domains of the Stokes operator. Now, by choosing the operator Q, which applies to nonlinearity, to be an identity in the space V, Q ends up being an unbounded operator with respect to the state space X, but we do get local Lipschitz property of the nonlinearity F from the state space X to this larger space V. So our next goal is to show that the linearized Navier-Stokes equations form a regular linear system. And the first natural step towards that is to verify semigroup generation on the state space X. Since we operate in this lifted state space X, we need some more smoothness from the body force Fv, namely it has been H1. And then we also here make use of the fact that we assume the boundary of the domain omega to be of the class C3. Starting from the semigroup generation result for the Stokes operator in the L2 type state space, we work our way to verifying that indeed the linearized Navier-Stokes equations on this lifted state space also generates a strongly continuous semigroup. And on top of that, if the viscosity constant is large enough, then the semigroup generated by A is exponentially stable, which is what we want. Finally, we note that in the definitions of the control and disturbance operators, we make use of these shape functions G and G apostrophe, which then lead to the control and the disturbance spaces being finite dimensional. So the actual control and disturbance inputs are just the terms U and UD. We have the following result regarding presenting the linearized Navier-Stokes equation as a regular linear system. So we consider the linearized Navier-Stokes equations around a steady state solution of the full nonlinear equations. And then we demand slightly more than L2 smoothness from the control and the disturbance shape functions. Now with these assumptions, taking any of the control operator, the disturbance operator, or the nonlinearity applying operator Q as the control operator of the triple of operators, we have that the triple is indeed a regular linear system in the lifted state space X. Because of the lifted state space X, we now have sort of a trade-off situation between the control and the observation operators. So usually an in-domain control with an L2 control shape function G would already be a bounded operator. But in this lifted state space, the control side becomes more unbounded. So these slightly smoother than L2 shape functions lead to an admissible control, which is not, however, a bounded control operator. On the other hand, a point observation is a quite unbounded observation compared to the weighted average observation options, for example. But for this lifted state space, even a point observation ends up being a bounded operator from the state space to the output space R. And now we can quickly return to just note that because the observation operator ends up being bounded, the lambda extension of it does not really play a role here. So the extension ends up being the operator C itself in this case. Putting our results together, we have that the controlled Navier-Stokes equations indeed do form a regular nonlinear system, and thus we can implement a low-gain error feedback type controller introduced by Natter and Benchman to take care of the output tracking problem, which we recall was a local and approximate one. This controller only requires information of the transfer function gains of the linearized systems. But since we are probably measuring gains from the full nonlinear system, it is worth noting that the robustness of the control solution means that the nonlinear system gains can indeed be used for the controller construction anyway, so we don't have to figure out the linear system control gains. Now returning to the achievable output tracking using this controller, we note that on top of the initial state of the fluid and the reference signal being small enough, we should also have a small enough initial state of the controller as well as a small enough disturbance signal. Then we choose a finite number of harmonics to be accounted for during the controller construction. These chosen harmonics of the reference signal and the system output will be matched, but the tracking remains approximate in the sense that other, typically higher, harmonics induced by the nonlinearity of the system will not be accounted for in the tracking. Finally, we note that the disturbance signals to be considered are of the same form with the allowable reference signals YR. Moving on to a numerical example, we consider the Navier-Stokes equations in a unit disk and chooses a viscosity constant 1/25, and then check numerically that the linearized system is exponentially stable for this choice. We control the horizontal component of the fluid velocity within omega u and disturb the vertical velocity component within omega d while observing the horizontal velocity component at the point psi p. We include the first 4 harmonics starting from 0 into the controller. Onto the simulation. Here we denote by blue the control region, by black the disturbance region, and by red the point observation. And then we have on the right side plots for the system output compared to the reference output, and then for the regulation error over time. Here we note that the color bar is chosen to be nonlinear to get a more indicative color scheme denoting the fluid speed within the unit disk. So for this simulation, we used MATLAB, and the spatial discretization for the Navier-Stokes equations was performed using finite element method, and then the time development uses Crank-Nicolson method with a Newton iteration. And as we can see, the convergence isn't too fast, but we also do not experience many overshoots, which is sort of a normal for the low gain control scheme. So you typically have somewhat slower output convergence compared to some other controllers, but you also don't suffer from overshoots. And by 120-second mark or so, you have very little error left into the system. Some of this is probably due to the numerical errors, but it's partially also from the approximate nature of the control. To recap, we formulated the incompressible Navier-Stokes equations subject to in-domain controller disturbance and a point observation as a regular nonlinear system. And the state space was chosen to be a smooth enough space so that the nonlinearity of the Navier-Stokes equation is locally Lipschitz in this case. We then implemented an error feedback controller to achieve approximate and local velocity output tracking for the Navier-Stokes system. To directly apply these results, one should consider a viscous fluid with a first order nonlinearity, and then the problem domain together with the boundary and boundary conditions should be such that the equation does not suffer from loss of regularity of the solutions up to the used lifted spaces.